we will have nice introductions, and then we will have a socialization of double degree program of UI and NAIST. So it is a good opportunity for students to get international insights, especially our collaboration with NAIST as our partner universities. So please welcome to Associate Professor Yaxiaer Yalikun Sensei. Time is yours. Please give applause.
Okay, thank you very much for your nice introduction. So my name is Yaxiaer Yalikun from Nara Institute of Science and Technologies. So seems like we have 10 students here, right? They're all master students. Are they still coming? Yeah, yeah. So what I mean is they're master student of the pharmaceutical department, right? So maybe you should know more about drugs than me, I think. Because actually my background is in mechanical engineering. So my background is mechanical engineering, and actually we developed systems, micro tiny chip-like system to accelerate or somehow contribute to the drug synthesis or some fundamental part of drug synthesis. For example, after the synthesis of the drug ingredients, you have to make it like a solid state. In that case, induced nuclearization and crystallization is very fundamental techniques for commercialize that kind of how do you say pharmaceutical process. So today's lecture, I would like to introduce some of our works. Actually, the main part of the work is conducted leading by our assistant professor Cili. His major is in crystallization and try to increase the conventional methods efficiency to how do you say to the next stage of chemical synthesis. So as you can see here, we have the chip-like device, and you can see there is a red light go directly into it. So actually, we have a very different type of device. We have developed those kind of devices for about 10 years. So I will not introduce all of them. I will pick two typical type of them and give you a step in introduction and talk about the potential application and their main advantages. So before I start my talk, I would like to first share a video. This video is to introduce our lab. All right. Okay. More fancier when I look at my PC. So it's some kind of a time lag there. But Anyway, so this is our major member in our lab. So Professor Hosoka majored in laser physics, and Assistant Professor Tsuri majored in electroengineering and actually using laser technologies to accelerate the crystallization process or nuclearization process. And we also have another assistant professor, Tanganomi. Actually, he's a biologist and tried to evaluate the drug uh, effects on the single cell level, from the single cell level to the zebrafish or individual levels. And associate professor me is because my background is mechanical engineering, so I'm good at making things or establish the system. So I will serve this biological and chemical purpose, try to install or driving a system to effectively achieve the chemical or biological purpose. And we have another research assistant called Dr. Okano. He is majored in the chemical engineering and also actively published paper related to the drug delivery. So let's go to the topic. So from my understanding of view, so actually in the traditional pharmacy process, there is a lot of problem. So one of the problem is actually the how to reduce the batch to batch variability. Do you know batch to batch variability? If you massively product drugs, you have to, the key process is about to those drugs and to pack it into the drug itself. Do you know you're familiar with that kind of process, right? Okay. Actually, that is quite important process. So crystallization will be taking major effects at this. And as you know, the crystallization process is very important, and 90% of current drug actually is in somehow has a tight relation crystallization process. So if you have a good and very unified and pure crystallization as control for the crystallization process, you can control the size, you can control the shape of the crystal itself, which is a pure ingredient of the drug, and you can control the exactly dissolving process. And also you can contribute to the uptake effects, which is this a good drug? Is this ingredient is effectively works? Actually, some part is related to its crystal qualities. But the current drawbacks is actually most of the traditional drug synthesis and crystallization, crystal generation process actually like cooking some kind of food with a very without a menu and sometimes you have to using the mysterious ingredients. So in that case, how to precisely generate the high quality, unified, controlled, continuously uh, continuously generate those kind of high quality crystal is become a major problem. Now, actually, there is a lot of process, both in small scale and large scales. They try to handle that. So, in my, in our view of the perspective, we are also try to control the environment directly. So, typically thinking, so what do you think? How to control the crystal quality by equipment. So usually we change the environment, like the temperature, like the concentration, or we have to using other methods to induce the look. When we induce it, we have to control it, and the local is affects in a very small area. Okay, is this all? Okay. Yes, okay. Please have a seat. Yeah, great, great. Glad to see a lot of young faces. Okay, it's okay. Okay, perfect. Okay, let's come back to the topic. So the problem in the current traditional pharmacy process. So usually in the pharmaceutical company, they try to put a lot of money discoveries and find some new ingredients workable and try to synthesize it in a very effective way. But before the formulation, you have to make it very pure. In most of cases, it should be crystallized. So they call that the crystallization process. And one of the key crystallization process is a nuclearization. So you have to have a very unified size control, shape control, the nuclear for induced crystallization in a relatively large scale. But the current method actually facing a lot of problem. Like here, there is a spatial and temporal chaos. Okay, they have to use a quite a large scale, and they use a batch-based method. So in each batch process, actually, it is quite difficult to control a very small local areas environment. So in that case, actually, it's leading to unpredictable nuclearization. Even there is a whole large batch, and if there is a very certain limited area has an unbalanced, not accept, predictable nuclearization effects, actually it influences the entire crystallization and finally will compromise the the formulation itself. And also current method usually apply temperature control or concentration control to use it as a traditional trigger to induce the crystallization or the nuclearizations. But if actually the precisely control the temperature is not so easy to be achieved. So if you can't do it perfectly, you actually can denature the sensitive biologics, and sometimes you damage the complex organics, which is actually will contribute negative to the drug's effects. And also to finally to achieve a very best control of the limit of the crystallization process, actually you have to try a lot of conditions and try to find optimized one with a proper course. So that is a major drawbacks for the current crystallization process, which is a major step for the pharmacy. So how can we solve this kind of problem? Actually, from our okay, so actually from our perspective view, our solution is combining two interesting technologies. One is microfluidic technologies, microfluidic chip technologies. Another is femtech lasers. So maybe you're not so familiar with these two technologies, do you? Or actually you're a master of the microfluidics or lasers, something? No, not yet. Okay, that's good because I am master of that. So I am willing to share it with you. So okay, so the key technology we call the microfluidic device. You can think that it is an extremely tiny channel system offering the precise control of fluidic flow. Okay, so you can precisely control the flow rate, the flow velocity, and internal chemical reaction by using this kind of tiny channel. And we use a femtosecond laser. Actually, it delivers very temporal and spatial limited trigger because the stimulation to the target solution, and we can precisely trigger nuclearization with the highest quality and controllability. So I'm just introduced two different technology. One is microfluidic technology, another is femtosecond laser technology. So I want to give a little bit deeper explanation about these two technology. So what is microfluidic? Do you know what is microfluidic? Small scale fluidic, right? So the micro is smaller than small scale, so it is very tiny. So in this scale, actually, there is a lot of amazing phenomena. Just like this one, you can actually we control three different type of liquid in a 100 micrometer channel. Okay, the width of the channel is about 100 micrometers. So among the channel, you can see there is no mixing at all. Okay, each layer is separated, controllable, and could be maintained for a relatively long time. So at this scale, you have the highest controllability of the liquid, of the fluidic situations. So in that case, we have an indicator, we call that Renault numbers, which is corresponding to the density and viscosity of the fluidics. So in the micro scale, the surface tension and viscosity governs the behavior of the fluidic, different from the macrofluidic. Because in the macrofluidic, the gravity and the inertia force is active majorly. So in this slide, you only need to remember that in a tiny scale channel device, you can perfectly control the behavior of the fluidic. Because most of the drag at its gradient or synthesis process, it is fluidic. So we can use our device to control the origin of the drag, which is kind of fluidic. So this is important, be remembered here. And for that kind of tiny little channel, seems like it is slow. It is like a very lack of productivity. But actually it is different. We can actually, if we apply enough pressure, we can flow the fluidic at the speed of 30 meter per sec, extremely fast. Okay, it is kind of difficult to understand, but in the micro scale, we also can do a very high flow velocity transportation of the liquid. So there is no need to worry about the massive productivity. So I give you a summary of the current microfluidic device. The interesting part is a microfluidic device typically should be fabricated by current most advanced semiconductor technology. Do you know? How do you use a PC, use a tablet, and the core chip in the PC or tablet actually fabricated by semiconductor fabrication technology, which is exactly the same technology we use to fabricate our microfluidic devices. That's why it has a micro tiny scale channel with high accuracy and perform very stably. So the microfluidic device itself actually fully utilizes microfluidic phenomena and fabricated by MEMS technology, serves chemistry and biology. And in single word, it is a total total engineering for total systematic engineering device. So I always use this slide to explain what is a microfluidic device to the biologist. So I think you also have to, how do you say, evaluate the drug's effects. You have to use biological samples, right? Using cell or tissue. No, you don't involve any kind of biological experiment. No, you do, right? So in that case, you have to use, most of cases, you use the 9612 dish device. But in that case, actually, the drug, especially for the fluorescent dye or something like that, it's quite expensive. But usually the target is very limited in numbers. So we invented a device only has a one of 100 size compared to the conventional device. It is a small and it is a, as you can see, it is a we only need a very less reagent. It is small, so saving space and saving energy to maintain the temperature culture of the cell. Then after that, it is actually increasing the contact surface area and enhance the efficiency of the drag. That is a typical example I'm showing here. This is only one example. So actually we have a lot of other type of device. And microfluidic device actually have been developed for about 3 decades. So now there is a lot of application for this kind of device, of course, including the drag development here. So other also including the biofuels, blood analysis, or a lot of technologies. So it is advanced now and also has a very rapid increasing speed. You know, the first rapidly increasing field is electronic vehicle and AI related hardware or software. The third one is microfluidic technologies. Why? People are wondering why it's growing so fast. Because recently, at about 15 years ago, the first organ on a chip device being invented. So we can use the patient's cell to create the specific organ of the patient on the chip. Because the pharmacy facing a single problem, because the human is quite different from each other, because that individual differences. To solve that kind of issue, because even the same ingredients actually affects differently on individual human beings. So maybe this is good drug for you, but actually it is damaging my organs in some kind of circumstance. So it will be the best to have your own organ tested by those kind of drug and try to find the most proper ingredients, proper components for your treatment. So in that case, the organ on a chip technology being established. So already we can we can establish your heart tissue, heart, liver, gut, kidney, and now brain, lung, a lot of, we can at least create the organ from your cells on a chip size device. And recent technology actually can do in the brain. So we can actually almost get the whole human on the chip systems. No, most of the pharmaceutical company in Japan and USA, they are actually reducing the number of animal experiments and shift to organ on a chip, human on a chip platforms. So with this platform, you can actually conduct the most, how do you say, highly effective drug evaluation, and you can make the customizable personal therapy just for yourself. That is a minimize the personal individual difference, which is a big, very big progress for the chip microfluidic device technologies. So for the most of people think maybe yeah, we capture something inside a plate-like chip, but actually it is not all for the microfluidic device. We actually can manipulate the fluidic at the top surface of the device. Okay, for the chemical guys, we want to make a different type of liquid together. We have them have the chemical reactions, and this is a different type of thing. But you have to use a lot of equipments like pipette, right? You have to move this a little bit, move that a little bit, and mix them together and see what's happened. But using our surface electronic device, you can actually did it much more faster and accurate. Okay, you can move the liquid, mixing them and separate them and mix them with another one at a few seconds, and with a higher accuracy of the volume. And also there is a droplet technology. Actually, you can have your capsule for every single cell, and you can apply to each capsule with a different concentration of the drug, and you can evaluate millions of conditions at single trial. Okay, that is very amazing technology. So they actually have students doing that kind of experiment, try to accelerate our current progress. So okay, that is microfluidic device. I think you are still with me, right? You're familiar. Now you're familiar with microfluidics. It is like a tiny chip, tiny channels. We put something into the channel. We control its environments. And what happened? So it is flowing. It is not good enough for the crystallization. So we have to trigger the liquid being flowing in the channel. So usually we can use the temperature, increase the temperature or decrease the temperature. But if you do that, actually it is you control the entire environment of chip device. So usually chip is like this size. So it is still not precise enough. So from that point, we have to introduce an external source of triggering the nuclearization or crystallization. That's why we have to use a laser. You're familiar with laser, right? You definitely use a lot of laser, different type of lasers. So most of you, I think, know what is a laser. It is actually short for light amplification by stimulated emission of radiation. Okay, so this is a light and travel forward. Also, so for some of you, maybe not familiar with a laser, actually I have a very, how do you say, simplified example of the laser. So the laser cavity structure looks like this. They have a two mirror at two sides of the light source. Okay. So when the light go forward and backward between the different mirrors, actually it go pass through the optical source, and the energy, the light keep coming out of the light bulb, and between this space, actually total is increased. At certain timing, the energy is accumulated to a certain level and go past a threshold. The light will come out of the one of the mirror and go outside of the two mirror systems. And the outside of this mirror system, we call that laser. But actually, for highly for high precise for the how do you say, accurate operation in a very tiny microfluidic channel, we actually cannot use the normal lasers. So in that case, so do you familiar? No, no. Okay, so yeah, that is new. Yeah, right. That's good. That's good. I'm looking forward to it. Okay, the femsecond actually is extremely short term of time. Okay, it is like 1 in 100 trillion of the second. You know, in light, it passed, the light speed is around 300K per sec, but femsec, the light only proceed about 300 nanometers. Okay, which means if we use femsecond laser, we can specifically control the material in a very small, limited area, let's say 300 nanometers. It's very tiny, highly localized effects. Okay, there actually, we have a lot of lecture to explain how to generate this kind of specific laser, and Professor Katsuki is an expert about femsecond lasers. So maybe if you go to our side, maybe Professor Katsuki will give you further deep discussion or lecture about laser physics. But today's lecture is about crystallization. So I'm just you just need to remember that femsecond is extremely small amount of time, and in that time period, light only proceed a very certain short distance. So what can we do? So when we focus the femsecond laser in a liquid, what will happen? As you can see, there is a lot of bubble, right? Actually, this is a, how do you say, real-time image. But if we use high-speed camera, we can see there is a, this is the focus point. When we irradiate single pulse of femsecond laser, there will be explosion, microscale explosion. In this explosions, you actually generated a bubble-like structure. And at the surface, there is a liquid phase and air phase. And between them, there is an interface. At the interface, there not just generates the force, because this is a micro particle and being pushed away, but today's focal point is not here. It's at the interface between liquid and air. So at the liquid and air, actually, it will induce the sound and it suddenly increase the concentration of the liquid. And if you have your gradients at the supersaturation state, suddenly increasing of the local concentration actually will induce the nuclearization of the gradients. Okay, at the very tiny interface, you actually trigger the nuclearization, and this is only happen very limited area. Let's say 400 nanometers. Okay, and if you can move the laser, or if you can move the fluid, you actually give a scanning laser continuous triggering the nuclearizations. And if you control the pulses of the laser, or if you control the flow velocity, you can keep giving the giving the trigger to the nuclearization itself. So that is our two key technology as I explained. So you're still with me, right? Microfluidic tiny channel and special type of lasers, and we combine them together. We use the laser and irradiate in a tiny little channel, and to continuously and with a very local controlled area nuclear inducing, then we can get a very high quality, high controllability of crystallization. And I always being asked at this stage, so why don't we just flow the liquid in the channel and try to use some fancy microfluidic effects to induce the nuclearization? As I said, if you want to use that, if you want to induce the nuclearization or crystallization only using the device, actually it is quite a broad area inducing of that kind of crystal. It is not accurate enough. But what about just how do I say? Let me say we can put the solution, the supersaturation solution, into a dish or something, and can't we just using the laser to scan on it and induce the crystallization or nuclearization? Actually, we can, but as you see, you cannot control the total amount that being scanned by the laser. Okay, by using microfluidic device, you can precisely control the behavior of the liquid, but if you put it in the dish, you cannot control the behavior. Maybe because of this kind of bubble, the flow is running away, or induce some kind of vortex flow or other kind of flow, and locally reduce the concentration at somewhere. It is lack of controllability of the liquid, and this is lack of controllability of the stimulation triggering. So we have to, it is only our method can solve both these two problems. Okay, so here comes our key topic. So why we need double degree students, why we need you to join our team. So we already have the microfluidic environment, which is my field, and we already have the Professor Hosoka, Professor Tsuri, so majored in the ultra fast optics, including femtosecond laser text, nanosecond laser text, picosecond laser text. And what we now need is pharmaceutical scientists to try to serve and try to fuse all our technology together to the next discovery, try to further enhance the current performance of the nuclearization and crystallization system for the pharmaceutical process. Okay, this is our current system. As you can see, tiny channel, special type of laser being irradiated into the channel, and we induce the highly controllable nuclearization of the ingredients. And after that, we can collect the sample and use them as a seed to give us a large scale crystallization, which we finally use serve the pharmaceutical purpose. This is current system. I think Indra is very familiar with this setup, right? Okay, so we have our microscope, syringe pump systems. We have our tiny chip there, and we have our huge fancy femtosecond laser at the behind of the microscope. Okay, so actually it is. I said it like it is. Yeah, definitely could be done, but actually it is a kind of hard work because we have to search for the optimal condition. Okay, if we irradiate laser with too much pulses or too much high pulse energy, actually it give us a little bit, very small, lot of the nuclearization. For some of the research, it is not preferred. Or we can reduce the power or reduce flow rate. We can give us a very beautiful large scale crystal and could be directly used as a drug. Okay, so in our research, we have to optimize every condition, including the fluidic condition and the laser operation. Here is a short summary why we're doing this. And compared to the previous method, our method is more like pinpoint spatial and temporal control, has a higher controllability. We can control the quality, the shape, the number of the crystal. And also there is no other disturbing environment like heat or vibration or anything. And it is continuous flow. It is suitable for massive production. We can continuously flow stuff. We just keep irradiate laser into it. We get our high quality of crystals and nuclear. And also it is kind of very easy to control the RH. I'm good at local controlling. It is quite good. So what we do is just have prepared some supersaturation liquid fluid channel ingredients of lasers, and the laser will generate the micro bubble, and there will over supersaturation phenomena generated at the interface between the air and liquids and start the acceleration and acceleration. Yeah, only four, only different cannot get to this kind of collision effect. You must combine them two together. Okay, so actually, I introduced two papers. So we tried different type of chemical ingredients. One is the sodium perlite, another one is the glycerin. And these two is a very common material used in the drug development process, I think. Okay, as you can see here, we have two major factors for the laser. One is phosphanidin, one is the efficiency. Okay, laser phosphanidin means energy for each pulses, and that is which comment pulses is really to the G. We can say there is a type of GP. Higher energy is the large scale, higher energy is more small, but most of it is slow, but and the object we cannot choose them all because it's a difference. We move on to new. Okay, also flow rate also contributes directly. You have a higher flow rate, you get smaller, but more nuclear, but here, and if you the flow rate, you look at the net larger crystal. Okay, so actually it is mathematical trade-off size and numbers. So here now, then after our system, we can try to translate those kind of physics to the real farmer formulation, and eventually maybe go to bring it to the production level. So if you enter in our laboratory, your PhD journey will be like this. You must have a very good pharmacy foundations. And you in our lab, we can share you with our optics, and we will try to, how to say, not teaching you, but we grow together as an innovative researcher. Okay, that is our imaging of our graduated students. Okay, so yeah, this is the future because of lack of time. This is a total summary of our technology. We use laser fluidics, again, using laser fluidics by tuning each condition, we can get a lot of high controllable crystal and nuclear. If you're specifically interested in some kind of details, you can check these two papers. This is our recent paper, so and you can read the paper and ask me if you have a specific concerns or even new ideas, or maybe you can, okay, we can maybe learn from each other. Okay, thank you very much. So let's move crystal together.
Okay, thank you very much, Sensei, for your insightful explanation and lectures. So it's time for us to do a discussion session. Please, if some of you have questions, raise your hand, and then yeah, we will discuss your questions.
Okay. Yeah, sure.
Okay, thank you very much, and very interesting discussion today. I'm Fatima. Unfortunately, I've done my PhD, so I couldn't I couldn't join your team. But anyway, I have questions regarding that. The first one is you show us like the what is it, like the picture of the sim of your system, right? Like one microfluidic chips, and then there's like a laser, and then there's like a chamber to collect all of the liquids, right? So I just wonder how fast the system actually could generate the nuclear, and how do you make sure that the nuclear that's produced is actually the same every time, like all the batches? Okay, that's all. Thank you.
Okay, thank you, Matt. That is a very excellent question. So about how do you say, productivity, productive capability. Actually, it is depends on the laser performance. And at the current stage, we only capable of how do you say, handling the sample at 1 milliliter per minute. Actually, it is a little bit slow, but because our film-second laser is not that, how do you say, powerful. And actually, you can, it is kind of trade-off between the laser spec and flow conditions. If you can, actually, you can flow it much higher, has a higher flow rate, and but you have to increase the laser pulses energy and also increase the irradiating total reputation rates. So if the most modern film-second laser system actually has our system is a 5 watt film-second laser. The most modern one is about 100 watt. So technically, by simple calculation, I think we can do it like a 20 milliliter per minute. That is quite a good, how do you say, capability to product this kind of crystal, right? Because this we only initialize the nuclear region, and the nuclear and those kind of small crystal could be used as a seed and to trigger the larger scale of the crystallization process that we could be used for massive product process. Actually, this technology, not using film-second laser, but using nanosecond laser, already being commercialized and being accepted by some pharmaceutical company, I think. But picosecond laser has only one drawback because there is thermal effects. So they cannot use for the kind of drug has a higher sensitive, how do you say? It cannot be used for the too sensitive drugs because the thermal effects will damage the organics, complex organic structure of the drugs, deactivate them. But if you can use film-second laser, actually he had much more less thermal effect. We can even apply this on the biological cell without killing it, right? Indora-san do that a lot, I think, right? You can actually give the cell level surgery inside the cell without damaging it. This is a very attractive point for this kind of microfluidic system combined with the film-second lasers. And second one, you talk about how the reproducibility, stable of the crystals. Actually, we did that in our paper. It's how do I say? Because in our system, okay, in our system, our evaluating method is to measure the longest access. It is quite stable most of the time. But for some other, I don't know, in the pharmaceutical field, how do you evaluate the quality of the crystal? So it depends on what kind of method you use. Some of them calculate from the volume, some of them calculate how do you say, total area surface. And because our side, the assistant professor Tsuri-san also is a specialist in the crystallization, so he's we use her method to measure the spec of the crystal by measuring the longest axis, which is quite stable. Almost most of the crystal within the error rates about 15%. That is much more better than conventional other methods, including the nanosecond laser methods. Okay, I think I answered your question, right?
Yeah, from pharmaceutical perspective, you could actually like check the stabilization through methods like XRD and other stuff, like to see the growth of the particles. Okay, yeah, thank you.
Your second PhD in our lab.
Okay. Itu nggak telat. Oke, bertanya dalam bahasa Indonesia juga nggak apa-apa ya. Nanti saya coba bantu translate atau Bapak Ibu dosen di sini juga.
Thank you very much for the time. A quick measure. My name is Aspari Rama. Konnichiwa. Welcome to Indonesia and welcome to UI. I'm very thank you very much for your insightful presentation. My next question is consideration the complex multi-step process in this microfluidic chip and femtosecond laser. In your experience, which specific stage is the most challenging and tricky to ensure the device perform reliable for drug crystallization? Thank you very much.
Okay, that is quite a practical question. So because we can trigger the nuclearization, but we have to wait for the growing of the crystal. Actually, it takes at least about 2 hours. So our entire, how this is, triggering process, could be done in few minutes, but we have to wait another 2 hours to finally verify the result. So we're actually quite afraid of during the waiting time. Is there any external stimulation we applied on the, how they say, productions and change the qualities? So to avoid that kind of problem, actually we establish some kind of specific device like a box, control the humidity, temperature, or even light, shut down all the light or use a certain wavelength of the light or something like that. Actually, compared to the device fabrication or laser operation, that part was the most struggle part for us. Yeah, we wish you can help us with some idea, maybe.
Okay, thank you very much, Sensei. Is there any other questions? Like, ada lagi yang lain? Nanya ya. Oke. Oke, ya, Ibu dulu aja.
Okay, it's me again. Anyway, so from your system, there's like you actually like flow the fluids, and then like the lasers like comes down, and then there's a collector. So I assume like the collector is still containing water. No, solution. Like the solution, is it?
How do you say it? Devour.
Yeah, and that yeah, it's empty bowl, but then there your solution flows, right?
Yeah,
And then
flows there.
then you collect it, then
Yeah,
it's
collected.
collected, and then
Them, yeah.
yeah, and then so it becomes like a solution containing the bubbles of nuclear. Is that right? Is it something that's collected? Uh-huh. Okay.
Can't see anything for using your naked eye.
Mhm.
But afterward, for a few minutes, you can see them.
Okay.
Most of it, from 1 milliliter per minute is not so fast. So actually, there actually no bubble being yet.
Oh, yeah. No, my question is like the collectors, after the lasering process, then when it starts from the nuclear to grow to be crystal, right? Like, how do you actually stop the crystallization process to make it like homogeneous, like for all the particles?
So, we actually measure the sample at a certain time after we collect it from the device. We can't stop the crystallization. So we fix the time, for example, 2 hours after our triggering the nuclearization, and measure the 2 hour interval, check how crystal it can be. And usually most of the experiment will be done about 6 hours or 8 hours. The crystal, how do you say? It will reduce the concentrations and make the liquid stop being crystallized.
Oh, so the liquid is the pure solution, liquid phase of the particles that want to be crystallized. I see. Okay, thank you.
Okay, thank you very much. So, any question from students? Okay.
Thank you for a really interesting presentations. I'm Salsa. I'm actually just finished my bachelor degree last year's. So this is a kind of new presentations, new things for me. I'm not even having a future imaginations about how well my PhD is gonna be. So if I interesting in this scope, what should I do first, actually? Because this sounds and looks really engineering. new setup that I never imagined, that I never seen before, even in my bachelor's degree. So how do I start, or what
That is
book
a
that I can read, or the theory that I can absorb like that?
yeah. So that is a excellent question, and actually, most of our students is exactly in your cases. So, because my background is mechanical engineering, Hosoka Sensei is in physics, and Professor Tsuri is in crystallization, and we have another faculty member is chemical biology. You can see everyone's background is different, exactly like you. You're pharmacy, right? So in that case, that is very good because we can share our experience and you can share yours. Because I am the engineering guy, but I have to find some application to serve. So that is good thing. You can make your pharmacy, how do you say, knowledge very, how do you say, you have to prepare it very well at the level of you can give us advice. Then we can beneficial from your knowledge and you will beneficial from our system. It is like a growing together system. Okay, because our student actually has a different background from biology, chemical, electrical, and that is a major merit of Nara Institute of Science and Technology. We're doing the research in a very fused area, not doing the pure biology, not doing the pure material, but combining them together, try to make a very innovative area and become the top of in that area, right? Actually, my the talk from now, I think that if I'm right, is introduce how do we find a chance to study in the Nara Institute of Science and Technology. Perhaps with your capability, you can get your master degree and apply for our double degree program. I assume maybe in the recent future, right? Hopefully, right? So in that case, yeah, the scholarship will be guaranteed and you have your plenty time to absorb every kind of information or knowledge you want. And also some of our students get a job opportunity in Japan, in the industrial, or I have one student in my lab, serve as postdoctor researcher, something like that. A lot of opportunity. But first you have to make your basic fundamental knowledge of pharmacy very good. Okay, that is the advice from me.
Okay, thank you very much, Sensei. Uh, maybe the question and answer sessions will be paused for now because there will be next session for Yasa Sensei to introduce NAIST. Yeah, please, time is yours.
Okay, so from now I will start next section. I will basically introduce the Nara Institute of Science and Technology, what kind of university we are and what is our strengths, and also what kind of people we want. And also I will introduce your alumni and also current Indonesian students work with us, stay with us, and enjoying life with us. Okay, so when we talk about Nara Institutes, hello. Okay, so when we talk about the Nara, so maybe you don't know where is the Nara, okay? So in that case, maybe some of you heard about the Osaka, maybe some of you heard about the Kyoto, and the Nara is kind of, actually it is the traditional capital of Japan in a very ancient time. But the very famous thing in Nara is kind of Nara deer, okay? You can touch the deer. I assume, I never touched it before, I'm afraid of them. Maybe you go to Japan, you touch them. It's interesting. And the good thing is that the Nara Institute of Science and Technology is in a quite a location that, how do you say, average location between these three famous spots. So you will never feel boring in our campus. But unfortunately, the institute is, how do I say, in a deep mountain where you can only focus on the research at the weekday, but at the weekend you can go out and have fun. So what kind of university it is? Actually, we are small in scale, but that doesn't mean we have a lack of research or education abilities. According to the ranking from the, Minister of Education, Culture and Sports Science and Technology, mixed. Okay, so we are the first two university get both high, rating as excellent in both research and education. Okay, the only two universities have been ranked excellent in this both subject. So you can see we are totally capable of doing good research and give students the best education. And different from the UI, we are quite compact institute. We only have 2,000 members, including the faculty member, about 300 of them. And the good thing is, as you can see, we have an information science building, biological science building, and material science building, and we are very close to each other. That is excellent environment to have combined research together. We can easily visiting each other in a few minutes. I extremely enjoy this kind of environment, so we can get professional advice from biologists just next to us and have our data or system be optimized by the professional in the information science. And we can offering the data to the information side, let them training their algorithm or a lot of other things. Here, actually, the idea to create this kind of university is really targeting the interdisciplinary integration of different field knowledge. Okay, so the original is more like majoring the three basic field together and try to create a whole new world for the science. And the good thing is actually we have so many students have very different background, but all the students can select those background select the program similar to their original background and learning new knowledge from different division or department of the same programs with different programs. And we also actually putting effort into the medical research. So the newly established is a Medilux Research Center. So we actually mobilize the AI technologies, try to give the patient the high effective diagnosis, or try to using AI technology to accelerate the drug synthesis or potential gradient searching or synthesis. A lot of that kind of research also being carried out. And also we have research about some brain research, try to recreate or establish the control mechanism for individual brains or assist those kind of disabled man by inserting some brain interface. And this is also another newly established center for data, named the Data-Driven Deforming Education and Research Center. So for the people who wants to deeply combine with information science technology, this program is the best for their choice. Okay, so because I am from the division of material science, I will give you a more detailed introduction of the material science department. We actually have about 18 core lab in our material science divisions, as you can see here. We have so many different types of research, including the organic, inorganic semiconductor devices or basic physics, combining with optics or polymer synthesis, or like engineering, combining with the laser technologies, microscope technologies, very different type of research. So I think we already have two candidates. We have one candidate apply for our laboratories. I think it is a very good match for the pharmaceutical background student come to our lab. As you can see, we have 5 different type of laboratory. And maybe you are very feel interested in the basic of the physics, so you can join this kind of lab. Actually, there is a two methods for students for selecting topics for the students. One is the professor will give you some option you can select, and another one is you can propose by yourself, which is more like you can utilize the current lab technology to achieve your purpose or specifically interested area. So it is quite free there. So if you want to do some physical stuff, you can apply for the physical-based lab, or if you want to do chemistry stuff, you can apply for the chemistry lab. Now our lab is more like a device-based lab. So if you want to, how do I say, make something and develop some system, or you want to combining more, play more with lasers, you can you can select our lab. So there is a more detailed explanation of each research topic. Actually, you can download this material from our website. It has a more detailed explanation. And you can see each professor's face. Maybe this professor is very gentle, but that professor is a little bit scary. So you can also check their faces and make your most satisfied thing. Okay, so our lab actually is this lab and combining with the laser microphysics. Another lab is like a more manipulation of different type of coherent optical properties. This is a pure physics. I use a laser as a probing tool to measure the physical properties. And some of the lab actually using very different type of equipments to elucidating the materials origin or something like that. Okay, so we have also have a lab that targeting the new material for the radiation measurements. We call that mass scintigraphy technologies, and also some kind of lab is focused on the carbon nanofibers. And this is the research that I talk about. You can fabricate little tiny device and insert it to the brain and control the individual's behavior by only changing the light wavelengths. Okay, they call that the optical genetics. So the individual brain cell is sensitive to certain wavelengths of the light. So you can insert a very tiny device into the brain itself and control the individual behavior. Here is using the right mouse. You can remotely using light to control its behavior. And also as a material science department, we have of course, we have the semiconductor technology, like fabricating the same film, flexible semiconductor devices, and also have a molecular science-based system and functional inorganic material sensor 6 labs, and we all have a all this lab is very suits for the pharmacy background student, I think. And also we have labs that is supported by the company. So if you're interested in, you also can search for them. As you can see, most of the research topic is related to the material, either synthesis new material, discovery new material, or to try to review the physical or chemical property of the material. Okay, the data science is data science part is actually one of my favorite type of research. You can minimize your wet experiment, but doing the simulation or calculation, try to find millions of possible combination and select them from by using algorithm, and you only do a very limited number of wet experiment to get what kind of specific component you want. So all this lab is a focus. They mainly put their main effort on the computational techs and try to minimize the effort to create a new type of material or a drug or antibody or something like that. About the research environment, I think we are among the top class of research facilities. So we have, of course, we have some typical clean room device, the chemical laboratory has a clean draft, of course, and we also have a few campus-wide computer cluster, which is now most booming part of the how do you say, the university. So we have our own supercomputers. We have a few computer cluster. So you don't need to worry about the computational resource if you want to apply any kind of computational based research. And actually, we have a Center for Material Research platform capable of analyzing, sensing, and reviewing the materials property and different scale. And also, we have a kind of most advanced fabricating system. We can fabricate about 10 nano scale objects by using our electron beam lithography systems. So if, how do you say, with this kind of semiconductor equipment, we can almost finish from design to commercialized stage of our devices. This is specifically for the semiconductor part. And also we are the part of the ARUM, which is actually purchasing the fancy equipment is not a big issue, but how to maintain them in good condition actually is extremely expensive. But fortunately, our university is covered by the ARUM Japan, so all the machinery will have extremely well maintained at good conditions, and we have over 10 technical staff specialists in charge of maintaining and training us. And in some of the case, even you can ask them to do the major part, and they are all specialists. So it will reduce your significant amount of time and let you mainly focus on your most novel part of the research. Okay, this is our international team material science department. Okay, we have people from France, China, Philippines, Australia, Thailand, USA. And actually, we hired an Indonesian student as postdoctoral researcher in my lab, so we need one more here. So the good thing is actually currently we have a totally 55 foreign students, and among them 28 of them are Indonesian. From almost half of the PhDs are Indonesian. So that means you will definitely never feel lonely there. You have so many, right, people. And of course, the scholarship is very important. So usually the max scholarship has the highest amount, which is actually very difficult to get. But fortunately, we have our NAIST International Scholar, which is almost the same amount as the max. But as you can see, there is quite a limit for the numbers. So you have to try hard to get past through the interview. But the good thing is, it is not only at NAIST level, but also at the division level. We have a research assistance allowance to support the basic life expenses in Japan. So the good thing is, from my personal experience, the tuition for the PhD almost fully waived. And with this amount of life support, I think it is sufficient for supporting your life in Japan. So if you're excellent enough, I think money is not be a problem, not gonna be a problem. And even the good thing is the double degree program. Also, we have the internship students from Indonesia, and we keep increasing the number. And the good thing is about 15 years ago, we already have a visitor from the University of Indonesia. So now we put more effort. We want to increase the number. We want to double it or triple it. We want at least 20 students visit us in a near, at least maybe next year. Okay, so that will be a good chances. At least we will, in that case, we will offer the transportation fee, the short-term stay, dormitory or guest house, and let you have a deep discussion with professors, maybe some small project, let the professor evaluate your capability. Okay, they are the graduated students from NAIST, Indonesia graduate student from NAIST. There are a lot of them. Where is the name of Indra? Oh, nice. Yeah, we are expecting you to go back and visit us. Oh. Okay, so this is Hanif, our new students, PhD first grade. Okay, this is a Katsuki sensei, and this is an Indonesian student from his lab, right? Okay. So because we have 28 Indonesian students, I can sure that each lab have at least one Indonesian student. So you not need to be worried you're being lonely. They have a lot of events, and the Indonesian people also holding party and also share me with their fruit. I'm quite enjoying that. I hope you do the same. Please share with me. Okay, so we also have the screen programs for the students. So we will soon launch the NAIST DMS Study Abroad Fair 2006. And this is specifically for the master students who has the intent to approach PhDs. So you have to contact the lab you are really interested in and submit some applications, and application deadline. It is actually now on the website. You can access to and check it for the details. And this kind of pre-screen internship actually is, we will invite you directly come to Japan and visit us, especially for the certain lab. And the lab professor will give you a precise evaluation. And most of the students will get guaranteed some kind of financial support. Okay, so this is yeah, we also have a financial support for master students, but actually it is much more difficult than PhD students, but we still have some. So if you are really, how do you say, excellent, I suggest you try it once. It is free, so try it. If you don't buy a lottery, you never get one, right? So, okay, so we also have a different program type for the pre-screenings. And this is quite similar. It is specifically for the student. This is max students enrolled at the next year. So you have to spend 1 year learning Japanese, I think. Summer. Okay, this is a specific tuition situation, so not. Okay, so I would like to introduce the dormitories. As you can see here, it is this is a dormitory for all the students. It is very cheap and fully has a air conditioner, desk, it's one room, and I think the kitchen is separated. It is a shared kitchen, but other thing is in the room, so it's still satisfied for most of the students, I think. And recently we established the share house type of dormitory. So there will be 3 students in a single room, and you will share in the dining kitchen and other thing together. Okay, so according to my personal experience, no foreign student not living in the dormitory. So your dormitory is quite well guaranteed. So no need to worry about where to live. And we also have other very different types of support for the foreign students, including the extra Japanese culture, event, parties, and yeah, a lot of activity, even I don't know well. Yes, quite a fruitful life there, I think. And the good thing is we are now at the quite final finalizing process about the double degree programs. Actually, we have already launched a lot of double degree programs with French, Thailand, Taiwan, and India. So I'm assume that we can soon add the UI to the list and welcome you to the NAIST. So that's all from my talk. So if you're specifically interested in one part, you can contact me or directly contact the international office. And all of the material actually is available online, so you can download them to search for the detailed information. Okay, this is the final slide, and there are all our professors. You can see them all here and select the most favorable professors. Okay, that's all for my talk. So if you have any questions, you can ask me now.
Okay, please give applause to Yaxiaer. Okay, students. So there was an introduction to NAIST. So if you have any question about NAIST or about future study in NAIST, please raise your hand. Yeah. Jadi. Hmm. Hmm.
It's okay. It's okay. You can secretly.
So about the screening program, what when will it be, when will the screening program be open? Oh, okay. Mm-hmm. Hmm. Oke, jadi ada kalau ingin kuliah di NAIST, nanti ada semacam screening awal gitu ya. Jadi nanti bisa internship juga visit laboratori gitu ya. Saya dulu juga seperti itu. Jadi selama 2 minggu ke Jepang, kemudian melihat laboratori, ngerjakan sesuatu di sana. Kemudian wawancara juga, presentasi, wawancara dengan profesornya. Kemudian ya ada pengumuman, ternyata alhamdulillah diterima, dapat beasiswa 150.000 yen per tahun tuh berapa? Sekitar berapa juta tuh? Sekitar 20-an juta, 18 juta ya. 16 juta ya. Sekitar 16 juta rupiah per bulan, dan itu cukup banget gitu. Bahkan untuk teman saya yang berkeluarga misalnya itu juga cukup gitu ya. Jadi di sana gitu. Terus enaknya kalau di NAIS bisa jalan-jalan juga di akhir pekan tadi ya, Nara, Osaka, Kyoto kayak gitu. Uh, I try to explain in bahasa Indonesia.
Thank you very much. That's perfect. So yeah, you can ask me after this lecture, I think.
Yes.
Yeah, I can give the more precise personal suggestion. Students have a less chance to get scholarship, but if you're excellent enough and you're rich enough, yeah, there is a high possibility because one of our students, Purio, actually self-funded student and being enrolled as a normal master student in our lab and go straight to the PhD course, stay 5 years. But first 2 years get no, how do I say, sufficient financial support. But he's rich, he don't care. But at the PhD stage, he is kind of well supported. So I think it's, how do I say, eventually actually is quite a good business for him, right? Actually, he get more than paid in first 2 years. So it's good strategy. But our interview for foreign students is exactly, we require the same quality compared to our Japanese students. So, but I think your UI student is excellent, right? So in that case, I feel
Yes, of course.
I think there is no problem. You can try.
Ya, jadi sebenarnya memungkinkan juga gitu ya. Kalau misalnya dari S1 langsung S3, jadi kalau misalnya punya, apalagi kalau punya biaya sendiri gitu ya. Itu kemarin ada pengalaman mahasiswa Indonesia namanya Prio juga di lab Yasa Sensei juga ya. Uh, dia lulusan UGM, terus kuliah langsung di NAIST S2-nya. Kemudian S3-nya juga di situ, terus sekarang dia kerja di Jepang gitu ya. Bahasa Jepangnya dari udah 5 tahun di sana, bahasa Jepangnya lancar, jadi bisa kerja di perusahaan Jepang gitu. Jadi mungkin banget, apalagi kalau teman-teman ya tadi ada biaya sendiri gitu ya. Untuk beasiswa kemungkinan baru ada yang S2 ke S3 gitu. For scholarship, it should be master degree to doctoral degree, right?
Scholarship.
Yes, for scholarship, this one master degree.
This one this is a for apply PhD course.
Yeah, master degree graduate to apply PhD.
No, yeah, so PhD.
Hmm. Nah, dulu saya dapat beasiswa ini, ya. Hmm.
So yeah, this is
Ah,
very good money, right?
yes. I I actually I got this uh no, yeah, I got this scholarship.
So you earn this money and they buy a house here, right?
I uh, I I I, bu- I bought a house.
Okay. So actually, the Prio, who is a how is it, graduate from our lab, find a job in Japan, and that is also quite a good salary, I think. Right. So he's quite now his Japanese is very good too. So
Hmm,
quite enjoy the life there.
ya. Ya, kerja di Jepang gajinya juga besar, lumayan. Jadi kalau bisa saya simpulkan tadi itu try explain in bahasa Indonesia ya. Kalau saya bisa saya simpulkan tadi itu kalau jadi di lab jasa sensei ini kan pakai laser ya. Jadi semuanya itu bakal novelty dan publishnya tuh di uh, ya di apa jurnal yang bagus-bagus juga gitu ya. Apapun yang kalian kerjakan tuh pasti novelty, nggak belum ada yang ngerjakan itu sama sekali gitu ya. Kayak tadi microfluidic chip gitu. Kemudian kristalisasi pakai laser gitu ya. Selama ini kalau reaksi kan random ya dalam satu tabung reaksi, tetapi kalau ada laser di situ kita bisa nunjuk nanti terbentuk kristal di sini ya. Apalagi kalau sintesis obat, tapi nggak dapat kristal kayak gitu ya misalnya. Itu kan bingung juga ya. Nah, dengan adanya laser ini bisa membantu untuk membentuk kristal kayak gitu ya. Atau tadi juga bisa manipulasi sel ya. Bisa milih sel mana yang mau dioperasi gitu ya. Bukan organ ya, sel gitu. Ya, jadi dengan apapun yang kalian lakukan dengan laser akan jadi hal yang baru gitu. Novelty-nya bagus gitu. Ah, ya dan kebetulan for your lab is there any opportunity to study in your laboratory?
probably more chances to visit the lab on site, and you can see the experimental environment, see the, how do I say, atmosphere, and secretly talk to the local Indonesian students, maybe share some secrets. Is that possible to stay here or something like that? That is a very nice choice, I think.
Oke, jadi ada kesempatan juga internship di sana ya. Oke, so Assoc, do you want to talk about double degree program? Oh, not the student, not now. Okay. Yeah, but maybe later. But I will give some insight for future. Yeah. So jadi ke depan juga akan ada double degree ya. Jadi teman-teman bisa bisa belajar daftar ke UI, kemudian selama setahun atau ya selama minimal setahun itu teman-teman bisa juga belajar di NAIST. Jadi nanti dapat 2 gelar, doktor farmasi UI sama doktor di NAIST gitu. Jadi kayak gitu. Jadi ke depan teman-teman yang berminat juga bisa daftar jadi dok dok apa ya double degree program in the
So,
future.
you actually you can be enrolled by the double degree program, which is actually still undergoing now, and we assume it will be established soon. So if it could be done, so the master student you graduate from here, you can join the University of Indonesia and the NAIST double degree program. You can get a 2 PhD degree from the UI and the NAIST at the same 3 year of period. Okay, so you have to, of course, you have to finish all the required curriculum subjects here. You have to stay here for about 2 semesters, or you can remotely be registered here for another extra 1 semester. And you have to spend about at least 12 months in Japan. And in Japan part, it will be, you can stay in the dormitory. And we assume that the student will get some kind of scholarship, either LPDP or maybe we through some brain pipe to accept students. We'll try our best to make sure they are well financial supported. And the most great thing is the student could have a double PhD degree within 3 year period. I think that quite attractive part of this system. And yeah, so we're still actually working on some detailed part. And when the most of the part is decided, I think I will visit here again, I think, in recent future, right? I hope this year, somewhere, I think. Yeah, at that time, I want to give a very deep discussion about the double degree program, what kind of people we really want, what kind of people we want them to have 2 PhD degrees, right? That is kind of a unique merits if you want to, how do you say, become the bridge between the 2 nations. I think that is very important.
Okay, thank you, Sensei. Okay, Oke, jika nanti jika misalnya mau bertanya habis ini juga boleh misalnya langsung datang diskusi dengan Yasa Sensei ya. Oke, oke, ya. Oke, is there any last minute question for you from you? Okay, I think the time is up. The time is up. Thank you very much, Sensei, for your lectures and information about NICE and scholarship opportunity there. And then, but before we close the sessions, we take a picture together. Please. Oh, plakat. Foto. Oh, okay. Wait, yeah. So we have Tapi langkat dulu Bu Kaita ya. So, Sensei, we will have a souvenir exchange for you that will be given by our manager of educations, Dr. Baita. Yeah. Uh, yang first. The cover page. Okay.